On October 16, 1971, the nuclear-powered submarine USS Halibut SSN 587 descended beneath the surface of the Sea of Okhotsk approximately 300 miles northeast of the Soviet naval base at Petropavlovsk on the Kamchatka Peninsula. The mission represented one of the most audacious intelligence operations ever conceived by the United States Navy. Commander Charles Moore guided the modified submarine through frigid waters that Soviet authorities considered absolutely secure, protected by the volcanic islands of the Kuril chain to the south, the mountainous Siberian coastline to the west, and intensive naval patrols that challenged any foreign vessel approaching what Moscow designated sovereign territorial waters. Soviet Pacific Fleet commanders operated with confidence born from geographic isolation and military supremacy in the region. They believed that American intelligence could never penetrate the Sea of Okhotsk to reach their most sensitive communications infrastructure. The presumption reflected decades of operational security doctrine emphasizing distance and depth as fundamental barriers to espionage. Yet as Halibut settled onto the seabed at 400 feet depth, American divers prepared to prove that Soviet confidence was catastrophically misplaced. The strategic significance of the Sea of Okhotsk to Soviet naval power could not be overstated. The enclosed sea measured approximately 611,000 square miles, roughly equivalent to Alaska's total area, bordered on three sides by Soviet territory, and accessible to the Pacific Ocean only through narrow straits controlled by Soviet military installations. Petropavlovsk served as home port for the Pacific Fleet's ballistic missile submarine force, including Yankee-class vessels carrying 16 R-27 nuclear missiles with ranges exceeding 1,500 miles. Soviet naval doctrine positioned these submarines as critical components of the strategic nuclear triad, providing sea-based deterrent capabilities that theoretically remained invulnerable to American first-strike scenarios. The submarines conducted patrol operations in waters where Soviet anti-submarine warfare forces maintained constant surveillance, where attack submarines hunted continuously for foreign intrusions, and where surface vessels enforced exclusion zones around sensitive facilities. Soviet communications infrastructure supporting these operations relied on undersea cables connecting Pacific Fleet headquarters at Vladivostok with naval facilities throughout the region. The cables represented mature technology dating to the late 19th century, when engineers discovered that copper conductors wrapped in waterproof insulation and armored with steel wire could transmit telegraph signals across ocean floors. By the 1970s, Soviet telecommunications engineers employed coaxial cables incorporating multiple conductor pairs that carried voice communications and encrypted teletype traffic. The installation connecting Petropavlovsk with command centers on the Soviet mainland ran along the seabed through the Sea of Okhotsk at depths exceeding 300 feet, following routes selected for optimal transmission characteristics and physical security. Soviet planners calculated that American intelligence services could not access cables positioned in territorial waters patrolled continuously by naval forces specifically tasked with preventing foreign espionage operations. The confidence Soviet commanders invested in cable security reflected reasonable assumptions based on historical precedent and operational realities. During World War II, British intelligence achieved remarkable success tapping German undersea cables in neutral waters, but those operations occurred in relatively shallow depths near coastlines where divers could work with conventional equipment. The Sea of Okhotsk cables lay at depths requiring specialized diving techniques and extended bottom time that exceeded capabilities of standard military diving apparatus. Soviet security assessments concluded that American submarines could not approach within detection range of the cables without triggering acoustic surveillance systems, that divers could not operate effectively at required depths in water temperatures near freezing, and that any physical intrusion into cable infrastructure would generate detectable electrical discontinuities alerting telecommunications engineers to tampering attempts. American naval intelligence pursued alternative assessments. Captain James Bradley, serving with the Office of Naval Intelligence, examined classified reports describing Soviet communications security practices and identified a critical vulnerability emerging from Soviet confidence in physical security. If Soviet commanders believed their cables remained beyond American reach, they might relax encryption discipline for routine communications considered operationally secure by virtue of transmission medium rather than cryptographic protection. The hypothesis suggested that unencrypted or weakly encrypted traffic might flow through cables presumed physically inaccessible to adversary collection systems. Confirming this hypothesis required capabilities the United States Navy did not officially possess, submarine infiltration into heavily defended Soviet territorial waters, precise location of specific cables on the ocean floor, and installation of sophisticated collection equipment without detection. USS Halibut represented the culmination of submarine modification programs begun in the mid-1960s under designations so classified that operational details remained compartmented decades after missions concluded. The submarine, originally commissioned in 1960 as one of the Navy's first nuclear-powered vessels designed to launch Regulus cruise missiles. When ballistic missile technology rendered Regulus obsolete, the Navy converted Halibut for deep ocean engineering and special operations. The modifications included installation of a deep submergence rescue vehicle chamber, a 50-foot cylindrical structure attached to the submarine's hull that outwardly appeared designed for rescuing crews from disabled submarines, but actually housed saturation diving systems enabling divers to live under pressure for extended periods and work at depths approaching 500 feet. The chamber incorporated hyperbaric living quarters, helium-oxygen-breathing gas systems, and transfer locks allowing divers to enter and exit the submarine while submerged without decompressing. The development of saturation diving techniques during the 1960s revolutionized underwater operations by eliminating decompression time penalties that constrained conventional diving. When divers breathe compressed air at depth, nitrogen dissolves into body tissues at rates determined by ambient pressure. Ascending to surface pressure requires controlled decompression, allowing dissolved nitrogen to escape tissues safely without forming bubbles that cause decompression sickness. For dives deeper than 200 feet, decompression time measured in hours exceeded actual working time on the bottom. Saturation diving employed different principles. Divers lived in pressurized habitats at pressures matching their working depth for days or weeks, breathing helium-oxygen mixtures that reduced nitrogen absorption. Once tissues reached equilibrium saturation with dissolved gases, divers could work at depth repeatedly without incurring additional decompression obligations. Final decompression occurred once at mission completion, typically requiring 24 to 48 hours regardless of total time spent at depth. The specific mission requirements for Operation Ivy Bells demanded capabilities exceeding even saturation diving systems. Divers needed to locate a specific cable on the seabed, install collection equipment without physically penetrating cable insulation, and ensure installations remained undetected by Soviet maintenance crews who periodically inspected infrastructure for damage. The National Security Agency developed specialized induction taps employing technology adapted from telecommunications engineering principles. When electrical signals propagate through conductors, they generate electromagnetic fields surrounding the cable. These fields contain the same information carried by the electrical currents but radiate outward into surrounding media. An appropriately designed sensor positioned near the conductor could detect these electromagnetic fields and reconstruct original signals without making electrical contact that would alter cable impedance or generate reflections detectable through time-domain reflectometry measurements that Soviet engineers employed for fault detection. The actual collection device measured approximately 20 feet in length, resembling a massive cylinder designed to clamp around the cable without compressing it. The interior incorporated sophisticated sensors including ferrite core transformers that coupled electromagnetic fields from the cable into recording circuits. The device included magnetic tape recorders capable of continuous operation for extended periods, battery power systems providing months of operational capability, and mechanical timers that activated recording systems only during periods when Soviet communications traffic typically occurred. The complete assembly weighed several tons in air, but achieved near-neutral buoyancy in seawater through careful engineering of internal volume and ballast systems. Installing the device required precision positioning and securing it against ocean currents that could shift equipment along the seabed. Halibut departed from Pearl Harbor in September 1971, carrying a crew briefed on cover stories describing routine patrol operations. The submarine transited northward across the Pacific, maintaining communications schedules and navigation patterns consistent with normal operations. Approaching the Kuril Islands, Halibut submerged to depths near 600 feet and reduced speed to minimize acoustic signature. Soviet hydrophone arrays positioned along strategic passages monitored submarine traffic, but Halibut employed sound quieting technologies that rendered it substantially less detectable than earlier generation nuclear submarines. The vessel crept through Kuril Strait passages during periods when oceanographic conditions created favorable acoustic propagation characteristics that degraded Soviet detection capabilities. Once inside the Sea of Okhotsk, Commander Moore navigated using specialized charts based on intelligence assessments indicating probable cable routes. Locating the actual cable required methodical search operations employing *Halibut's specialized sensors. The submarine carried side-scan sonar systems that generated acoustic images of the seabed, revealing features including the slight elevation where cables rested on bottom sediment. The search continued for days as *Halibut conducted systematic surveys across areas where intelligence analysts calculated cable routes most likely followed. The breakthrough occurred when sonar operators detected a linear feature running across their survey track. Halibut positioned directly above the contact and hovered, while crew members deployed additional sensors confirming the target represented an undersea cable rather than geological features or discarded debris. The diving operations commenced with saturation chamber pressurization to match ambient pressure at 400 feet depth. 6 divers rotated through working shifts, exiting the submarine through transfer locks and descending to the seabed via guidelines attached to Halibut's hull. Working in near-total darkness illuminated only by handheld lights, divers located the cable and began installation procedures. The extreme cold, water temperatures hovered near 35 degrees Fahrenheit, penetrated even through heated diving suits designed for polar operations. Narcosis from helium-oxygen breathing mixtures at high partial pressures impaired cognitive function, requiring divers to execute precisely rehearsed procedures with minimal improvisation. The installation consumed multiple shifts as divers maneuvered the heavy collection device into position around the cable, secured mechanical clamps, and verified sensor alignment. The completed installation appeared unremarkable to visual inspection, a cylindrical housing wrapped around a section of cable with no visible penetrations or physical alterations to infrastructure. Soviet maintenance crews conducting periodic cable surveys would observe only a section of their own cable, perhaps with what appeared to be marine growth or sediment accumulation around protective housing. The collection device activated according to programmed schedules, recording signals propagating through the cable and storing data on internal magnetic tapes. Halibut withdrew from the Sea of Okhotsk through the same passages that provided entry, conducting exit operations during periods when Soviet patrol patterns created temporary surveillance gaps. The intelligence windfall exceeded even optimistic projections. When NSA analysts reviewed the first tape collection retrieved during a subsequent mission, they discovered that Soviet communications discipline was far more lax than anyone anticipated. Soviet commanders transmitted substantial volumes of unencrypted voice communications discussing operational matters, maintenance schedules, personnel movements, and technical problems with equipment. The traffic included conversations between submarine commanders and Pacific Fleet headquarters, status reports on ballistic missile submarine readiness, notifications of vessels entering and departing port facilities, and discussions of training exercises and patrol operations. Even encrypted traffic provided value. Analysts studying message volumes, transmission timings, and communication patterns derived intelligence about operational tempo and alert status without breaking encryption. The operation continued for nearly a decade with periodic tape retrieval missions conducted by *Halibut and subsequently by USS Parch SSN 683, another specially modified submarine carrying even more sophisticated collection and diving capabilities. The missions occurred approximately monthly, with submarines penetrating the Sea of Okhotsk, locating the collection pod through acoustic beacons, and retrieving recording tapes while installing fresh units. Soviet naval forces operating in the region never detected these intrusions. The intelligence collected informed United States strategic planning at the highest levels, providing insights into Soviet nuclear submarine operations, maintenance problems affecting fleet readiness, and operational procedures that American attack submarines exploited during trailing missions against Soviet ballistic missile boats. The operational security surrounding Ivy Bells was extraordinary. Only personnel with specific need-to-know received briefings on the program. The submarine crews themselves understood they conducted special operations, but did not necessarily comprehend the specific intelligence targets or collection methods. NSA analysts processing the collected intelligence worked in facilities with access controls exceeding those for routine signals intelligence programs. The classification level designated exceptionally controlled information, restricted dissemination to individuals specifically authorized by program managers. The security measures reflected understanding that disclosure of Ivy Bells would immediately end the operation and potentially compromise other collection programs employing similar techniques. The operation's exposure resulted not from Soviet detection, but from betrayal within American intelligence infrastructure. Ronald Pelton had worked as a signals intelligence analyst for the National Security Agency between 1965 and 1979, handling classified materials related to various collection programs including Ivy Bells. Personal financial problems accumulated during his NSA employment, with debts from failed investments and expensive lifestyle choices exceeding his government salary. When NSA denied his requests for financial assistance, Pelton resigned in July 1979, owing approximately $65,000 to creditors. His financial desperation led him to contact Soviet intelligence services offering to sell classified information in exchange for payment. On January 14, 1980, Pelton walked into the Soviet embassy in Washington, D.C., and requested to speak with security officials. KGB officers stationed at the embassy recognized immediately that Pelton represented an extraordinary intelligence opportunity. A former NSA analyst with detailed knowledge of American signals intelligence programs desperate enough to commit espionage for money. During initial meetings, Pelton described various collection operations he had worked on during his NSA career. When he mentioned American access to Soviet underwater communications cables, the KGB officers understood the strategic significance. They authorized immediate payment of $35,000 with promises of additional compensation for detailed information about collection methods and locations. The intelligence Pelton provided enabled Soviet counterintelligence services to identify the specific cable being tapped in the Sea of Okhotsk. Soviet naval security officials organized salvage operations disguised as routine cable maintenance. On a date in 1981 that remains classified, Soviet ships positioned above the cable section, identified through Pelton's information, and deployed remotely operated vehicles. The salvage operation recovered the American collection pod intact. Soviet engineers examining the device discovered sophisticated electronics, recording equipment, and according to some accounts, a small metal plate stamped property of the United States government. Whether this marking represented intentional psychological operations, dark humor by American engineers, or simply standard government property accountability remains unclear. Regardless, the Soviets possessed incontrovertible proof of American cable tapping operations in what they considered sovereign territorial waters. The Soviet response involved immediate security upgrades to communications infrastructure throughout sensitive operational areas. Engineers examined all undersea cables for evidence of tampering, installed improved fault detection systems capable of identifying electromagnetic anomalies associated with induction taps, and increased encryption requirements for communications previously transmitted with minimal cryptographic protection. Soviet naval security organizations launched investigations attempting to identify how American forces located specific cables and penetrated defenses to install collection equipment. The investigations never determined the operational methods. Submarine infiltration techniques and diving capabilities remained beyond Soviet assessments of American capabilities. American intelligence services did not immediately recognize that Ivy Bells had been compromised. The loss of collection access appeared gradually as Soviet communications patterns changed and previously productive intelligence sources dried up. Counterintelligence analysts reviewing the degradation could not determine whether operational security failures, Soviet technical improvements, or policy changes caused the losses. The truth emerged only after Vitaly Yushchenko, a senior KGB officer, defected to the United States in August 1985. During debriefings, Yushchenko described a former NSA employee who had provided Soviet intelligence with information about American technical collection programs. The description led investigators to Ronald Pelton. Federal agents arrested Pelton on November 25, 1985. The espionage investigation accumulated substantial evidence through surveillance, financial records analysis, and testimony from Yushchenko. Pelton's trial in 1986 exposed significant details about Ivy Bells despite government efforts to protect classified information. The jury convicted Pelton of espionage on June 5, 1986, and the judge sentenced him to 3 concurrent life sentences plus 10 years. Pelton's motivation remained purely financial. He expressed no ideological sympathy for the Soviet Union, only desperation to resolve his debt crisis. The damage he caused cannot be quantified precisely, but the loss of Ivy Bell's collection eliminated one of the most productive intelligence sources against Soviet strategic submarine forces during a critical period of Cold War tensions. The legacy of Operation Ivy Bells extended beyond the specific intelligence collected. The operation demonstrated American technical capabilities that Soviet military planners had dismissed as impossible. The successful infiltration of heavily defended waters, location of specific cables on the seabed, and installation of sophisticated collection equipment without detection revealed operational capabilities the Soviets could not counter. Even after discovering the tap, Soviet forces could not prevent similar operations in other locations. American submarine technology, saturation diving systems, and intelligence support capabilities meant that any undersea cable potentially remained vulnerable to collection operations regardless of physical security measures. The principles validated through Ivy Bells informed subsequent intelligence operations. The U.S. Navy continued developing specialized submarines for sensitive missions, including USS Parch Asterisk, which became the most decorated ship in Navy history through classified operations that earned the vessel 9 Presidential Unit citations. The saturation diving techniques refined during cable tapping missions enabled other underwater operations, including recovery of equipment from crashed aircraft and disabled satellites, installation of sensors in strategic waterways, and reconnaissance of foreign underwater infrastructure. The induction tap technology evolved into more sophisticated collection systems capable of operating at greater depths against improved cable designs. The exposure of Ivy Bells through Pelton's espionage highlighted vulnerabilities in personnel security and insider threat detection. The NSA implemented enhanced financial monitoring programs, improved psychological evaluation procedures, and strengthened compartmentation of sensitive programs to reduce damage from potential future compromises. The recognition that financial desperation motivated Pelton's betrayal rather than ideological conviction led to expanded employee assistance programs and more aggressive intervention when personnel exhibited financial stress indicators. Soviet reactions to Ivy Bell's discovery reflected deeper anxieties about American technical intelligence capabilities. If the United States could tap cables in the Sea of Okhotsk, what other collection operations might be ongoing against infrastructure Soviet planners considered secure? The uncertainty generated expensive defensive investments including enhanced cable encryption, improved physical security for communications infrastructure, and expanded counterintelligence operations attempting to identify American collection methods. The psychological impact potentially exceeded the actual intelligence losses. Soviet commanders could never again assume that distance and depth guaranteed security. The confidence that Soviet Pacific Fleet commanders invested in the physical security of their undersea cables dissolved when engineers raised the American collection pod from the seabed. The presumption that territorial waters and geographic isolation provided sanctuary against American espionage collapsed when they understood that U.S. submarines routinely penetrated their defensive perimeters. The operational security doctrine assuming encryption was unnecessary for physically protected communications failed when NSA analysts read transcripts of unencrypted conversations discussing nuclear submarine operations. Operation Ivy Bells proved that in the technological competition defining the Cold War, American ingenuity consistently defeated Soviet assumptions about what capabilities their adversary could achieve. The lesson that emerged from 400 feet beneath the Sea of Okhotsk remained clear. There exists no sanctuary when one side possesses the will to accept extraordinary risk and the technology to execute seemingly impossible operations.